One of the most noticeable features about the ocean, if you say to someone that you're going to go to the ocean or you have in your mind an image of the ocean, is the crashing and motion of waves towards the shore. The waves themselves, though, are an interesting phenomenon. They actually reflect the movement of energy through the water rather than the flow of water itself. So we'll talk about that some in this short lecture series here. First of all, you have to distinguish between free and forced waves. In a free wave, the wave is formed and then it is no longer influenced by that causing force. So if you throw a rock into a pond, the rock bloops in there and you see the little ripples, the little waves that move away from where you threw that rock in there. That's a free wave because the rock made the initial wave and then it stops. A forced wave is different. The force there is maintained. We just got through talking about the influence of the atmosphere, moving winds on the ocean, creating currents. They're also responsible for creating generic waves in the ocean. So in the oceans, we have both, but we mostly have the forced waves. If we classify waves, we can talk about them in terms of size. And first of all, you have this situation that we call glass. That's where water sits perfectly still and flat and there's no motion, no wave at all. If you start blowing on water, you create the smallest little waves, capillary waves. Here I've called them CW. Eventually, if you keep blowing, they build up to the point where they are gravity waves. And then larger still is what we call swell. For both capillary waves and gravity waves, the restoring force is such that the water wants to fall and return to the glass situation. Swell is the set of waves that arise where they've built to the point where this energy flow is moving on its own through the water. If we consider the size of waves, everybody wants to talk about, well, how big a wave was it? How big a wave did you see? How big are the waves at the shore right now? How big of a wave did that surfer ride? The size of the wave is directly proportional to three things, meaning as these three things go up, the size of the wave goes up. First of all, the wind speed. This makes sense. The wind is blowing faster and faster. It's throwing more and more energy. There's higher transfer of energy to the water. Wave size increases. The length of the blow. The length of the blow here is in terms of time. And obviously, again, if wind blows for 1 hour, it creates wave of a certain size. But if that same velocity of wind blows for 10 hours, it can create larger wave size. And then finally, there is fetch, and that is the total distance over which that wind blows. If that wind is blowing straight ahead at 10 kilometers an hour for 500 kilometers, okay, it creates a wave of a certain size. If that same wind is blowing over a distance of 1,000 kilometers, 1,500 kilometers, at the end of that distance of which it's blowing, it's creating larger waves. Waves themselves are modeled by this figure here. A wave motion is actually a passage of energy, and what happens, it creates these oscillations of water. So if you've seen some object floating on the water and a wave goes through it, it looks like it's bobbing up and down. It is. It's doing that because the individual water particles are making these clockwise circular motions. Notice here, the energy wave is traveling from the left side to the right side. It forces these oscillations at the surface. Those oscillations at the surface then force oscillations below them, and those force below them, and so on and so forth. Notice that the circles of oscillation get smaller. That's because energy is transferred and there's loss of energy with depth. And you reach some point where it's called the wave base, where basically the influence of the surface is no longer felt. Okay? The orbit diameter increases in size or decreases in size all the way to what's called zero. We have to talk about a few ways we measure waves. Again, I can't emphasize enough, this is going to be important on the exam. You'll need to know these terms, what they are. So first of all, there is L, the wavelength. That is the distance from the crest to another crest, or from a trough to another trough, basically the same distance. H is the height. That is the distance from the bottom of the trough to the top of the crest. And here you see that that is the diameter of this oscillation motion. We can also then take those two primary measures and divide one by the other to create a wave steepness profile. This is the height divided by the length. If we think about some other things here, if water depth is d, little d, then the depth to the wave base is L divided by 2, or half the wavelength. So if you have a crest to crest distance of 10 feet, then the bottom of the wave base is going to be 5 feet. 10 divided by 2. So it's a simple sort of cutting it in half. If you know the wavelength, then you know the depth to the wave base. The importance of the wave base is this. By creating waves at the surface, you're moving water down through the water column, and this water moving can interact with the bottom. It interacts with the bottom in a couple of ways. It gets slowed down by the bottom because it literally feels the bottom of the water, but it can erode the bottom. If this is a wave in the middle of the open ocean, well, obviously the bottom of it is feeling nothing. It's not touching any kind of rock or sediment or anything like that, so it's not eroding it. It's just energy has petered out to nothing. If, on the other hand, you are in shallow water towards the shore, this is going to touch and affect the bottom. It actually starts making waves crash. They tumble forward. And so we call these progressive waves. They move forward. These other two terms, frequency and period, I'm not going to ask you any specific test questions over them, but they might be choices on a on an exam. We have this interesting phenomenon called the longshore current to think about. And in a longshore current, if you have waves that are meeting the shore at some oblique angle, like the cartoon is showing. I mean, sometimes it looks like waves are coming in right parallel to the line of the shore, and sometimes they do. But generally, there is some angle between the two. What happens is the waves crash in at that angle, and then backwash is perpendicular to the shoreline. So waves come in and crash, and then the backwash goes out that way. The net result is these large red arrows here, the longshore current. So the water that crashes over here sort of gets forced up, back, in these looping motions shown on the shore. The net result is water is transferred that way. It's a longshore current. Now, the longshore current itself, because these waves are interacting with the bottom of the ground, remember the wave base is touching here, so it's eroding. The sand grains at the beach are picked up, and they also are moved this way. And so the movement of the water we call longshore current. The movement of the sand or the sediment particles we call the littoral drift. this is also moving parallel to the shoreline. And the littoral drift can create all kinds of features like this. Notice that we have this longshore current. In this case, it's moving down in the opposite direction of those previous slides. But what it's doing is it's migrating and moving the beach. There is a motion of the sand sort of to the bottom of the slide here, creating this spit, and ultimately it will close off this next bay like it's done over here. Longshore current and littoral drift doesn't continue forever. At some point it is forced outward towards the oceans themselves, and it makes the water flow out and then makes the clasts flow out. Here's a picture of part of the Southern California coast. You can see Santa Barbara, Santa Monica, and then way down here is San Diego. And the red lines are the longshore current with littoral drift. They reach the headland, one of these areas where the land sticks out into the water. The water and the sand gets forced seaward into these ocean basins. Here's another one, another one, another one. So the Southern California coast is a whole series of these cells where longshore drift operates, littoral drift operates, and eventually it gets thrust out into the deep ocean. The Californians use this for convenient places to dump their garbage at sea, because if you dump your garbage where these down black arrows are shown, that water, that garbage, is going to flush it away from the land out to sea and take it down to depth. How do we stop littoral drift? Well, why would we want to stop it in the first place? Mostly because it tends to erode away and remove beaches. And we have a primary economic incentive to have those beaches there. Think about every beach town you've ever been to. They market that beach. Big sandy beaches. Come and play. They want that sand to stay there. And so we've created a whole series of infrastructure, things we build, and you've heard them go by names like seawalls, jetties, groins, etc., etc. In these diagrams here, they're shown as these, for this situation, these vertical stripes. And what they do, if you've got a current now that's coming from left to right, it's making that sand move. If you put an obstruction here, it blocks it, and the sand gets deposited. You get a wider beach here. But if you get a bonus here, you have to pay for it elsewhere, because on the other side of any of these human-built structures, it increases erosion on the other side. So if you add beach here, you're going to remove it here. So usually you see all kinds of high value properties over here, big hotels and resort areas where they've paid to have these structures built to enhance their beach. And over here would be the lower rent district of towns like this. Here in the lower picture, you see they've built a whole series of these seawalls. And again, what it does, it enhances the beach on one side, but it removes it. It has a negative effect. It erodes it on another side. Another feature of wave motion is that there is such a thing called headland erosion. As waves come in to the shore, let's say here they're coming in roughly parallel to the shore, they will hit these areas of land that stick out into the water first. We call them headlands. And then the energy is wrapped around these headlands such that the bulk of the energy is spent as crashing waves on these headlands, and then you have these delightful little calm bays in between. So here you have giant rocky cliffs at the headlands, and here you have nicely deposited quiet bays with beach sands. Here's an old aerial photo of essentially this thing where you can see the wave fronts coming in, and they they wrap around, they intensify, such that, look at the waves way down here in the bottom. They're kind of looping back, looping around, so that all of this energy gets intensified in the headland area. Here's an actual photograph. You can see one big headland in the distance, another headland in this middle area, and you're standing on a third headland. The action end of the waves is really operating to erode away these headlands, and then here you see these quiet bays with simple low surf coming in and depositing sediment here. If we look at a cartoon of the time evolution of these things, you see that you have big headlands sticking out like so in figure A. In figure B, this intensification of the headlands is causing headland erosion. At the same time, it causes deposition in the bays between. If you think several thousand to hundreds of thousands to millions of years later, these headlands have gotten washed back even more now that there's just a whole series of little islands called stacks out here, and the shoreline is getting straighter and straighter until ultimately you get a nice straight shoreline, and then longshore current starts up again on this thing.